Okay, let's talk a little bit about natural resources and energy economics. Since 1800, the world population, from 1 billion to 7 billion, and the standard of living is approximately 12 times higher. So, with a higher population, then demand for waters has increased, demand for resources such as fish has increased, demand for land has increased, and energy. Okay, so Thomas Malthus, uh, you know, thanks to him, economics was deemed a dismal science, and that's because of some of the predictions he made that didn't look very favorable for the future. Long story short, he basically said that with the increase in birth rates, that all the resources would be used up and um, population would run out of food and then begin to starve and die off. In reality, this is not what happened. Okay, so what ended up happening is that with an increase in living standards, is that the total fertility rate began to decrease, and in fact, the replacement rate has also decreased. Okay, so replacement rate, in order for a country's population to replace itself, each woman needs to have 2.1 children. And the reason it's above two is because, well, first, we look at two because two children are needed to replace, you know, two parents. And then point one because not all children make it to adulthood and be able to reproduce. They might not have kids, or they might die before they have a chance to have kids, unfortunately. And that has been the result of modernization, is that not only have fertility rates dropped, and in fact many have dropped below the replacement rate, so populations of certain countries, as we will see in the next slide, are actually decreasing over time, but also there's better access to healthcare, and death rates have also fallen, and people are living longer than ever. One explanation as to why modernization leads to lower fertility rates is, in the past, parents needed to have a lot of children because children were needed to work the farms, and also because death rates were higher, they needed to ensure that at least two children would make it to adulthood. But now that children are no longer needed to work farms, they are a higher cost. It's very costly to raise a child and put them through school. And so what we're seeing is people are having less and less kids because children have become a cost instead of a labor unit. I know it's a weird way to look at kids, but that's what children's purpose was back when we were more agricultural society, is they were considered units of labor. Okay, so we can see um, none of these countries here quite have the replacement rate needed of 2.1. You could see Hong Kong is very low at 1.09, and of course their one child policy act, has something to do with that for sure. Had a huge influence. And we can see Australia's 1.77, Canada 1.59, Russia 1.61, France a little higher. Okay, it's almost replacing itself at 2.08. Okay, and so over time, what we've seen is that despite population growth, despite due to population growth, commodity demand has been increasing, and also per person consumption of resources has been increasing. That commodity prices are falling because commodity supply has grown faster than commodity demand. Okay, and so we can see this over time, that there's a downward trend of commodity prices. Okay, and so when we talk about our resource use sustainable for the future, where we have enough resources for future generation, and it seems like we will. What we've seen is that demand for resources has leveled off a bit because of declining birth rates in countries that use a lot of these resources. So a lot of energy resources um, are used in the United States, and the United States birth rates have started to decline, and same with Europe. However, you do need to look at the fact that in other areas of the world, birth rates are still very high, and so their populations are increasing. And so, even though resource use has leveled off and it's expected to decline in the United States and Europe, for example, that in Africa, for example, in the Middle East, resource consumption is expected to rise. Okay, but overall, we can see here that total water use is here in the red, and per person water use, it peaked here in around 1980, and then it has remained steady throughout that time, and actually per capita water use has fallen. And just a little side note, this chart is for water consumption for the United States. Okay, so we saw that, you know, demand for resources has leveled off in rich countries, but demand for resources will increase in poorer countries, and they may not have enough local resources to satisfy the increased demand. And so, it's a challenge to find a way to move resources to places that will need them more of in the future. There needs to be more institutions developed and to help transport these resources, or else shortages may happen. Okay. This is for the United States, and so per capita energy use has also leveled off. It hit its peak right before 1980 and then remained steady, and also total energy use has leveled off since the year 2000. It's kind of remained steady then. Also, per capita trash generated, which shows us how much solids is consumed in total trash, and so we can see per person that per capita trash has also leveled off really since around 1990. All right, BTUs is British thermal unit, and it's the amount of energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. And the BTU per person has been declining steadily since 1990, and what we see is GDP is rising. So what this chart is telling us is that energy is becoming, or the use of energy is becoming more efficient, meaning each person is able to make more goods and services while using less amounts of energy. Okay, so there is a challenge in being able to provide energy at the lowest cost possible. And, energy demand is highly variable. An electric plant, has to provide energy for thousands and thousands of home and businesses, and they need to provide energy for 24 hours a day, 7 days a week. But energy demand is different during different times of the day. So usually at night, energy demand's a lot lower than during the day. So usually the type of power plants that will minimize operating costs usually have the highest cost in terms of construction. And construction is considered a fixed cost. And so in order for them to supply energy at the lowest possible cost, they have to operate at economies of scale and work at full capacity. But sometimes a plant might be able to work at full capacity if, the peak demand is 20 megawatts per hour, but maybe at other times, if it's an extremely, let's say, hot summer, and this has happened in Houston before, where we've been asked to conserve energy, the megawatts per hour demanded exceeds full capacity. And so, one solution could be that they build another plant, but that would be, a huge use of resources, would be very expensive. because we don't always need that second plant to be working. So that fixed cost would be very high, and it would just raise overall energy prices. So one solution is that electric companies will utilize different types of generation technology. So they would use some coal, some natural gas, some nuclear, some renewable, etc. And so this allows them, for example, to build a natural gas generator to supply excess energy once the original plant's at full capacity. And even though the cost would be higher per hour, the cost to build is much lower. And so this can help meet all sorts of demand for energy, and the overall cost is lower than if they were just to build more of the same type of plant. The likelihood of running out of energy is low because we have many sources of energy. So we typically think of, oil running out, and oil tends to be cheap energy, especially lately. If you've been keeping up with current market trends, oil, is $35 a barrel and below some days. But we do have other sources of energy. They may be more expensive, but they are there, so it doesn't seem like we will run out of energy anytime soon. But we should consider some of the environmental impacts. For example, using coal as energy, coal emits a large amount of carbon dioxide, and this can contribute to global warming, which has been a huge concern to scientists and to policymakers. There are new technologies that allows coal to be burned more efficiently, so it doesn't emit so much carbon dioxide. However, it is very expensive. So usually coal's energy is priced high in order for the companies to make profits that they can then use to buy more efficient and cost-saving coal burning technology. So conventional oil is cheapest. It's economically viable at $20 a barrel. By economically viable, it means that the cost of producing the oil will be less than the revenue that the oil will bring in. So at $40 a barrel, it is profitable for companies to use tar sands and use it as ethanol here. At $50 a barrel, it is profitable for companies to then exploit shale oil and sell it, and so on. You can see that biodiesel is the most expensive here. Okay. So policies for extracting resources look to maximize net benefits, and that's when the total dollar value of all the benefits minus the total dollar value of all cost is either zero or positive. And so these decisions also take into account present versus future consumption. What's understood is that the more we consume today, the less there will be in the future, and the more that is saved today, the more that can be consumed in the future. But there is a distinction because this applies more to non-renewable natural resources, and non-renewable natural resources are resources that have a fixed supply. Okay, they can be renewed, but it's so slow that it wouldn't be within one person's lifetime that the whole supply will be replenished. So resources such as oil, coal, metals, these are considered non-renewable natural resources. So the more of non-renewable natural resources that are consumed today, the less non-renewable natural resources there are to be consumed in the future. Whereas renewable natural resources are resources that can renew themselves. So forest wildlife, for example, they grow back, and they can grow back at moderate rates. So we can enjoy these resources forever if they're managed well and properly. Optimal resource management takes into account the net benefits uh, today if the natural resources are extracted and used versus also the net benefits in the future. So what we find is that if prices of that resource are expected to go up in the future, then less will be extracted and used today, and more will be extracted and sold in the future, because the future will, since there's a higher expected price, will command a higher profit. If future prices are expected to fall, then more will be extracted and sold today, since that resource can be sold at a higher price today and bring in a higher profit. Non-renewable resources have an opportunity cost called user cost, and this is the cost that the more of the resource that is extracted and sold today, the less of it that is available to be extracted and sold in the future. Whereas renewable resources, they can replenish themselves, and so there's a steady stream of these resources in the present and in the future. Non-renewable resources don't replenish themselves, or they do so at a very slow rate. So the more that is extracted today, the less there is to be extracted in the future. So, like mentioned earlier, if the demand for these resources is expected to be higher in the future, therefore they could be sold at a higher price and bring in less profits, then less will be extracted today. Okay. Also, if a company doesn't have well-defined property rights, if they don't really own the land and their lease is to expire to not be renewed, then the incentive is for the company to extract as many resources today and sell it, since they might not have access to that land in the future. Okay, so for firms that extract natural resources, the total cost curve is their extraction costs plus their user costs. Again, user cost is the opportunity cost that a firm faces of reduced future extraction because you're choosing to extract a resource now. Okay, so the more they extract now, the less they will have of that resource to extract in the future. Okay, so if a firm only looks at their extraction cost, then they will produce at point A, okay, and at quantity O right here. Okay. However, okay, if it does take into account user cost, and they understand that the more they extract now, the less resource there will be to extract in the future, therefore lower profits in the future, then they will produce at point B. Okay. And then the difference between the total cost curve and the extraction cost is the user cost over here. Okay, so the firm won't produce anything greater than Q1 because the cost, okay, after Q1 is greater than the price per unit that they're receiving for the resource. Okay, they want to make sure that total revenue, which is P times Q, is greater than or equal to total cost. So anything above Q1, okay, is not profitable, so they wouldn't produce. So let's say if price were to increase, okay, then they would produce over here at Q3, okay, since their revenue per unit is higher, okay, they can produce more because that higher revenue can cover higher costs as well. And then if the price were to drop, then less of the resource will be extracted and produced because it's not as profitable. Okay, so let's say right now the firm is producing here at point, let me use a different color, point A. Okay. But let's say they receive information that they expect future production of the resource to be more profitable. So let's say they expect, in this case, oil, and they expect oil prices to rise in the future. So what happens is this raises the user cost. Again, that's the opportunity cost of producing more now. And so the opportunity cost of producing more now would be higher because you're giving up higher future profits in order to produce now. Okay, so an increase in user costs would shift the total cost curve up. Okay, and so where price here intersects the new total cost curve, this will, okay, and so now the firm's extraction output falls to Q1. Okay, and if the user costs were to fall, then the reverse would happen. Okay, the total cost curve would shift back down, and then quantity extracted would increase. Property rights has given people an incentive to preserve resources, and so we're going to look first at elephant preservation. So in the 70s and 80s, the elephant population was drastically declining in Africa. Elephants are being poached for their ivory tusks, very valuable. And in a couple of countries like Botswana and Zimbabwe, locals were given property rights over the elephants. Okay, and so the owners of property rights preserved their elephants, and the population of elephants increased in those regions, which helped prevent elephants from becoming extinct over there. So in the regions where villagers did not have property rights for elephants, it was very competitive. Whoever could kill the elephant first would kill it and then get the ivory tusk. There was no incentive to spend time or money to breed more elephants and preserve elephants and breed them, because since there was no defined property rights, you could spend all that time and money, but someone else might take your elephant since it technically was not your elephant. There was no property right assigned to it. But once property rights were assigned to elephants, then local villagers started using elephants for other purposes. For example, they would, take tourists on safaris to see the elephants, and so this gave locals a constant stream of income. And other people would sell a hunting right to sports hunters, and so this would prevent poaching. This would also control the amount of elephants that were killed in hunting, and the elephant population was preserved. Now, with forest management, a very similar story. In countries with no property rights, deforestation is happening rapidly. And the reason this is because, again, no one owns the land to the forest, so it's, first come, first serve. So these loggers are coming in, they're chopping as many trees as they can, and there's no incentive for them to plant new trees because someone, they might take the time and money to do so and harvest, but someone else might come in and take their tree. So if I go and I find a tree, I chop it down, and let's say I plant another seed, someone else might come in and take that tree. Since there's no property rights, that tree technically does not belong on me or on my land. But in countries where their forests are private properties or they're strictly government regulated, then there's an incentive to replace trees that are chopped down with seeds. Okay. They want, since they own the land, they want the steady income that trees bring, that wood brings. Okay, and so they have an incentive to, once they chop down trees, to plant seeds and grow new trees. And what we also see is that when forests are privately owned or regulated by the government, then what we see is that trees are harvested at their most optimal point, and we'll see this in the next slide. So usually it's anywhere between 50 and 100 years. So usually closer to 100 years, it's the best time for trees to be chopped down because they have reached their maximum size. Whereas in places without strong property rights, it's kind of, you have to get to the tree before someone else gets to the tree. So sometimes they're chopped down, or many times they're not chopped at their optimal size. And so, it leads to inefficiency. Okay, you can see where rapid deforestation is happening in, for example, Nigeria and Ghana. And then you can see how in Iceland, Puerto Rico, there's been an increase in the percent of land covered by forests. And again, there's, better defined property rights. So there's an incentive for the forests, once trees are chopped down, there's an incentive for new trees to be grown. And so, they worry about the long-term sustainability of their business. And so they invest in their land and make sure that they're replacing trees. Okay, so the rapid growth stage for a tree actually happens between 50 and 100 years. Okay. So to get the maximum amount of wood, it's best to harvest a tree right around here. Okay. At 100 years. Okay, here after 100 doesn't really grow much, but before that, okay, the tree's not at optimal size. Okay, so a fishery is a stock of fish or other sea life that can be thought of logically distinct groups. So, for example, a place where you can find Newfoundland cod or Alaskan salmon, those would be considered, a fishery. And in the next slide, you can see the top 10 U.S. fisheries and how much they're worth in dollar terms. It's difficult to assign property rights because if the fish is in the ocean and swimming, it doesn't belong to anyone. It's only once the fish is caught that there's a defined property right. Whoever catches the fish then has property right over the fish. So this creates a competitive environment among fishers. Whoever, the more fish they catch, then the more private property of fish that they own. And so we don't want overfishing to happen because then it will deplete the supply of fish and cause what is known as a fishery collapse when the fisheries population is set into a rapid decline. Okay, and they're being fished faster than the fish can reproduce. So governments have tried to prevent overfishing through certain ways. One would be, they shorten the length of fishing season so that way during off-season fish can reproduce. Also limiting the number of boats as well. But, both of these policies failed. With the shorter fishing season, what ended up happening is fishers bought bigger boats so they can harvest more in that short period of time. And then also limiting the number of boats, same thing. They would just buy bigger boats as well so they can take more area than the next guy. A policy that has been more effective is total allowable catch, and this limits how much fishers can get of a certain fish. So, like, for example, one company might only be allowed 100,000 tons per year of fish. However, this policy has encouraged competitiveness among fishers, and so, a lot of these fishers get bigger boats to try to catch as many fish as possible before their limit is reached. A more efficient and effective way of regulating fishing that has lowered costs is the issuance of individual transferable quotas. And so these are smaller quotas, like it could be like 1,000 tons of a certain fish or species, or 2,000 tons that can be harvested during a time period. And once the individual catches that fulfills their ITQ, and since they're smaller quotas, usually they don't need the bigger, more technologically advanced, expensive boats. They can have smaller, more efficient boats. And once they fulfill their ITQ, then they can sell their fish in the market to a company that is willing to pay a higher price for it. So companies can fulfill their total allowable catch and buy other fishermen's ITQs. And what this has resulted in is lower costs and more efficient outcomes, and the social benefit of less competitiveness. Okay, so the top 10 fisheries in the United States, we can see sea scallop. The market value of all the sea scallops caught in 2010 was $455.6 billion. Lobster, about $400 billion. And then we have walleye, pollock, sockeye salmon, and so on. Both Atlantic tuna and red hake are victims of overfishing. And so you could see how they peaked. Atlantic tuna early 80s, and red hake in the mid 80s, and then after that, they collapse, especially red hake. They catch maybe 1 ton a year, usually less of red hake now. Okay, and this concludes chapter 17.